Redundancy is achieved with hard drives through a set of standards called RAID, or Redundant Array of Inexpensive Disks. Although this can technically be achieved through software, in most cases a RAID controller is needed. This is hardware which sits either on the server's motherboard or on a plug-in expansion card. The operating system in the server is designed to connect to hard drives and assign drive letters, for example, like the C drive on your PC. The RAID controller sits logically between the operating system, for example Windows or Linux, and the physical hard drives. There are a number of RAID levels which offer a combination of performance and resilience. Common levels used in servers include 1, 5 and 6. This can become a complex area, and if you are in doubt, always seek advice from technical pre-sales. In many cases, your customer will know what he wants, and all you need to do is capture this information so pre-sales can help you configure the quotation. Over time, as you quote for more servers, you will become comfortable with RAID. Let's cover the more common options to get you started. RAID 1 is probably the simplest to understand and is often used in servers to protect the disk from which the operating system loads and which is subsequently used for its own storage needs. The descriptive term for RAID 1 is mirroring. This is where a second disk is kept as a mirror of the first. This is a function of the RAID controller. The operating system is not aware of the second disk and is fooled by the RAID controller into seeing just the original disk. The benefit of doing this is that if the disk fails, the controller can instantaneously switch to using the second disk. So despite a disk failure, the system keeps running and no data is lost. The downside of RAID 1 is that it can only protect one disk, meaning capacity is limited. It is also relatively expensive, in that the disk is doubled to provide resilience. If, for example, the two disks are 300 gigabytes, we would say the raw capacity is 600 gigabytes, while the usable capacity is 300 gigabytes. To protect large volumes of data, a popular choice is RAID 5, which can be described as striping with parity. For this to work, a minimum of 3 disks is required. These drives are grouped by the RAID controller into a pack. The operating system sees just one large disk. The RAID controller breaks the ones and zeros of the data into chunks and inserts extra ones and zeros called parity bits in such a way that the data is protected from errors. This is then written or striped across the disks. To illustrate this, let's assume our data is 1, 0. We need to insert a parity bit based on a rule which says that each chunk of data must have an even number of ones. So in this case, we must add a 1. Now we will write the data to our disk pack by striping across the physical disks. This process works for any data. We are using 1, 0 simply as an example. Now that we have striped the data across the disks, we are in a position where any single disk can fail, yet the RAID controller can reconstruct the original data. Let's take the example of the second disk failing. Data cannot be read from the second disk. However, the controller knows that across the 3 disks there must be an even number of ones. Given that disk 1 and 3 both contain a 1, the data on disk 2 must be a 0. In this way, the operating system can continue running and without data loss. RAID 5 is popular because the overhead for parity protection is 1 disk's worth of storage. So if we have 3 300 gigabyte drives, the usable storage is 600 gigabyte, whilst the raw storage is 900 gigabyte. RAID 5 is not limited to 3 disks. A pack can be formed of as many disks as the controller can manage or that can physically fit into the server chassis. So with say 10 disks, you have 9 disks worth of usable storage and 10 disks worth of raw storage. The more disks, the more efficient the use of space and the lower the RAID overhead. Due to the way striping is implemented, although the data is written logically across the drives, in practice the 3 drives are written to at once. This makes RAID 5 faster than writing to a single disk. The more disks in the pack, the faster data can be written. This benefit is made possible by having cache memory on the RAID controller. The data is captured extremely fast into memory, then written to the hard drives in parallel. Depending on the number of disks and the required performance of the system, RAID controllers come with different amounts of cache. Take advice from your pre-sales expert to specify the right amount. The main limitation of RAID 5 is that it only protects against a single disk drive failure. Until the faulty disk is replaced and the data on that drive is rebuilt, the server is at risk. This could be hours or even days. Another drive failing would mean loss of all data across the RAID pack. RAID 6 is similar in concept to RAID 5, but includes 2 parity bits, meaning 2 extra drives are required. RAID 6 is justified when data is more critical or when the RAID pack is formed of a high number of drives, because in this scenario, the probability of 2 drives failing increases. The theoretical minimum number of drives for RAID 6 is 3, but in practice it is normally used for bigger RAID packs. A further consideration for your server is that if a disk fails, it will clearly need replacing. Some drives are fixed, meaning that the server needs to be powered down to make a replacement. This downtime may not be acceptable to your customer, in which case they will need to pay a little extra and go for a chassis which supports hot plug drives. These are typically located on the front of the unit so that they can easily be replaced while the system is powered up. No downtime.